Welcome to this coding walkthrough. Today, we'll tackle problem number 276, paint fence. This is a classic dynamic programming problem where we explore how to efficiently paint a fence with certain constraints. Let's dive in and break it down step by step. The problem asks us to paint a fence with end posts using k different colors. However, there's an important rule to follow: no more than 2 adjacent fence posts can have the same color. This means that while painting the fence, we need to carefully manage the color choices so that the pattern remains valid. Given the input values n, which represents the number of posts, and k, the number of colors available, the goal is to calculate the total number of ways to paint the fence while adhering to this rule. For example, if n equals 3 and k equals 2, we'll determine how many valid arrangements of colors are possible. In terms of input format, n is an integer between 1 and 50, and k is an integer ranging from 1 up to 10,000. The output will be a single integer representing the number of valid ways to paint the fence, given the inputs. For the input where n equals 3 and k equals 2, the output is 6. This means there are 6 valid ways to paint the fence while following the rule that no more than 2 adjacent posts can have the same color. Let's break it down. With 2 colors and 3 posts, the valid combinations are as follows: color 1, color 2, color 1, color 1, color 2, color 2, color 2, color 1, color 2, color 2, color 1, color 1, color 1, color 1, color 2, and color 2, color 2, color 1. These combinations demonstrate how the rule is maintained, with no 3 consecutive posts sharing the same color. Similarly, for the input n equals 1 and k equals 3, the output is 3 because with just one post, we can paint it using any of the 3 available colors. Now, when n equals 2 and k equals 4, the output is 16. This result accounts for all possible valid arrangements of 2 posts with 4 different colors, ensuring that no 2 adjacent posts share the same color. Since there are multiple colors available, the choices expand significantly, giving us a total of 16 combinations. Here, the explanation highlights the importance of managing adjacency rules while still maximizing the use of the available colors. These examples illustrate how the problem scales with different values of n and k, emphasizing the need to calculate combinations systematically while adhering to the constraints. The constraints and edge cases of the problem help us understand the boundaries of the solution. For example, n can range from 1 to 50, and k can go up to 10,000. A special case occurs when k equals 1, if there's only one color, the output is 1 if n is 1 or 2 because it's still possible to paint the posts without violating the rule. However, for n greater than 2, the output becomes 0 because it's impossible to paint more than 2 posts without repeating the same color consecutively. Additionally, the solution must be efficient enough to handle large inputs, such as when n is at its maximum value of 50 and k is 10,000. The output must also fit within the range of a 32-bit signed integer. This means we need to account for edge cases like minimum input values, single color scenarios, and very large inputs to ensure the solution remains robust and efficient. To approach this problem, we start by considering the brute force method. The intuition behind this is simple: we generate all possible ways to paint the n fence posts using k colors, ensuring that no more than 2 adjacent posts share the same color. This involves recursively trying all combinations of colors for each post, while checking the constraints at every step. If we encounter a violation of the rules, we backtrack and explore other combinations. However, due to the sheer number of combinations, this approach has an exponential time complexity of O, k to the power of n, where k is the number of colors and n is the number of posts. Additionally, it requires O, n, space for the recursion stack. As a result, this method becomes computationally expensive and impractical for larger inputs, making it unsuitable for solving the problem efficiently. To address these limitations, we turn to a more structured approach using dynamic programming. Dynamic programming allows us to tackle this problem more efficiently by breaking it into smaller, manageable subproblems. The key observations here are that each post can either be painted the same color as the previous one only if the last 2 posts don't already share the same color or a different color. To keep track of this, we define 2 states: same, which represents the number of ways to paint the current post the same color as the previous one, and diff, which represents the number of ways to paint it a different color. Using these states, we derive transition relations: same is equal to the previous diff, and diff is calculated as the sum of the previous same and diff, multiplied by k1, to account for all the other color choices. The total number of ways to paint each post is simply the sum of same and diff. With this framework, we initialize the states for the first post, iterate through all the posts to update these states using the transition relations, and finally return the total ways for the last post. The dynamic programming approach significantly improves both time and space complexity. The time complexity is O(n), as we only need to iterate through the posts once. The space complexity can also be reduced to O(1), since we only need the current and previous states to calculate the next values. This space optimization is achieved by using two variables instead of an entire DP table. Specifically, we maintain two variables to store the previous same and diff values, updating them iteratively for each post. With this optimization, we maintain the efficiency of the solution while reducing resource usage. This makes the approach not only optimal but also scalable for larger inputs. Importantly, there are no significant limitations with this approach under typical constraints, making it the most efficient solution to the problem. Ultimately, we chose the optimized dynamic programming approach because of its balance between efficiency and simplicity. The key insight was recognizing that we only need to keep track of the previous states, which allowed us to eliminate the need for a full DP table and reduce space complexity to O(1). This approach also retains the time efficiency of O(n), making it well suited for large inputs. While the brute force approach is conceptually straightforward, its exponential time complexity renders it impractical except for very small inputs. The trade-off with the DP approach is that it requires a slightly more complex implementation compared to brute force, but the efficiency gains far outweigh this drawback. Among the possible solutions, the optimized DP approach stands out as the most practical, striking an excellent balance between clarity, performance, and scalability. By leveraging state transitions and minimizing space usage, we achieve an elegant and highly efficient solution to the problem. To solve this problem, we need to figure out the number of ways to paint in fence posts using K colors, while ensuring that no more than two adjacent posts have the same color. This means every configuration must respect the constraints of adjacency. Starting with a brute force approach, we can define the problem recursively. Each post can be painted with one of K colors, and the recursive function will explore all possible combinations to ensure the constraints are met. For a given post I, we choose a color C, and then validate it based on the colors of the previous two posts, I1 and I2. This recursive exploration systematically attempts to generate all valid configurations while adhering to the rules. To design the recursive function, we define a helper function paint, I, previous one, previous two. Here, I represents the current post being painted, while previous one and previous two are the colors of the last two posts. For the base case, if all posts are painted, meaning I greater than n, the function returns 1 because it represents a valid configuration. For the recursive case, we iterate over all K colors, and for each color C, we check if it satisfies the constraints. Specifically, the color C is valid if it's different from the previous color previous one, or if it matches previous one but not previous two. If valid, we recursively call the function for the next post with updated parameters, summing up all valid configurations. The computation starts with paint 1 minus 1 minus 1, where no posts have been painted yet. However, the brute force approach has exponential time complexity, K to the power of n, because it evaluates all combinations, and its space complexity is O(n), due to the recursion stack. To optimize the brute force approach, we can use dynamic programming, which avoids redundant calculations by storing intermediate results. We define a DP state DP, I, same, where I represents the current post, and same indicates whether the color of post I matches the color of the previous post I1. The transitions are straightforward. If the current post is painted a different color, same equals 0, the number of configurations is DP, I1, 0, plus DP, I1, 1, asterisk, K1, since there are K1 valid color choices. If the current post is painted the same color as I1, same equals 1, the number of configurations is simply DP, I1, 0, because this is only valid if I1 was painted a different color from I2. The base cases are DP, 1, 0, equals K, as the first post can be painted any color, and DP, 1, 1, equals 0, as the first post cannot match a previous one. This approach significantly reduces redundant computations compared to brute force. To compute the final solution, we sum up the values of DP, n, 0, and DP, n, 1, which represent all valid configurations for painting in posts. The time complexity of this approach is n*k, because we compute transitions for each post in n steps with k operations per post. The space complexity is n if we maintain a full DP table. This method highlights key insights about the problem, such as the importance of recursive constraints, which naturally lead to overlapping subproblems. The number of valid color choices at each step depends on the colors of the previous two posts, which simplifies the state space. The base cases also play a crucial role in initializing the DP solution, as the first post sets the foundation for subsequent configurations. To further optimize space complexity, we can use a rolling array instead of a full DP table. Since each state only depends on the results of the previous state, we only need to maintain the values for I1 and I. This reduces the space complexity from n to O1. The rolling array approach stores the DP states in two variables, previous and cur, which are updated as we iterate through the posts. In terms of data structures, recursion with memoization can also be used to optimize the brute force approach, storing results of paint, previous 1, previous 2, in a dictionary or 2D array. For the DP solution, a 2D table DP, same, can be used to store the number of ways to paint up to post I for both states of same. However, the rolling array is more efficient in terms of memory usage, making it ideal for large inputs. When considering edge cases, small values of n or k provide quick solutions. For example, if n equals 1, the result is simply k because there's only one post to paint. If k equals 1, the result is 1 if n equals 2, since all posts must be the same color, but 0 if n2, as this violates the constraints. For large values of n, the DP approach ensures efficient computation without exceeding time or space limits. It's also crucial to handle impossible configurations, such as when k equals 0, where the result is 0 because no colors are available. Overall, transitioning from brute force to dynamic programming provides significant efficiency improvements by leveraging overlapping subproblems, while rolling arrays further optimize space complexity. This makes the solution scalable and well-suited for a wide range of input sizes. This implementation solves the paint fence problem using a bottom-up dynamic programming approach. The goal is to calculate the number of ways to paint n fence posts with k colors such that no more than two adjacent posts have the same color. We start by handling base cases. If there are no posts, n equals 0, the result is 0. If there is only one post, n equals 1, it can be painted in k ways. For two posts, n equals 2, there are two scenarios: both posts have the same color, k ways, or they have different colors, k*, ways. The variables same and diff track the number of ways to paint the last two posts with the same or different colors, respectively. For example, same starts as k, all posts the same color, and diff as k*, adjacent posts different. For larger values of n, starting at 3, we iterate and update same and diff. The new diff is calculated as same plus diff, k1, which combines the previous configurations where the last two posts were either the same or different, multiplied by k1 for the new post's color. The new same is simply the previous diff, as for the last two posts to be the same, the previous pair must have been different. Finally, the total number of ways to paint all n posts is the sum of same and diff, reflecting all valid configurations. This approach is efficient, with n time complexity and O1 space complexity, as only two variables are updated in each iteration. This is the Java implementation of the paint fence problem, following the exact logic as the Python solution. The code makes use of variables same and diff to handle the cases where the last two posts are painted the same or differently. The iterative loop ensures that we calculate the total number of ways efficiently. Key differences include explicit type declarations for variables and the use of Java's class structure. To solve this problem, we start with n equal to 3 fence posts and k equal to 2 colors. The goal is to determine how many ways we can paint the fence so that no more than 2 adjacent posts have the same color. First, we address the base cases. If n is 0, there are no posts to paint, so the result is 0. If n is 1, we can paint the single post in k different ways. Since n is 3, neither of these cases applies. Next, we initialize two variables. The variable same represents the number of ways to paint the last two posts with the same color, which is simply k, or 2 in this case. The variable diff represents the number of ways to paint the last two posts with different colors, calculated as k multiplied by k minus 1, which gives us 2. Now we begin iterating for I starting at 3. For I equal to 3, we first store the current diff value in prev_diff. Then, we calculate the new diff as the sum of same and diff, multiplied by k minus 1, which evaluates to 4. Finally, same is updated to the value of prev_diff, which is 2. After completing the iteration for I equals 3, we move to the final calculation. The total number of ways to paint the fence is the sum of same and diff. Adding these values together, we get 2 plus 4, resulting in 6. This means there are 6 ways to paint 3 posts with 2 colors while ensuring no more than 2 adjacent posts share the same color. Now, let's consider a new example where n is 4 and k is 3. With 4 fence posts and 3 colors, the base cases are checked again. If n is 0, the result is 0, and if n is 1, the result is k, which is 3. Since n is 4, these conditions do not apply here. We move to initialization. For n equal to 4 and k equal to 3, same is set to k, or 3, and diff is calculated as k multiplied by k minus 1, which evaluates to 6. The iteration begins at I equals 3. For I equal to 3, prev_diff is set to the current value of diff, which is 6. The new diff is calculated as the sum of same and diff, multiplied by k minus 1. This evaluates to 18. Same is updated to the value of prev_diff, which is 6. Next, for I equal to 4, prev_diff is updated to the current diff, which is now 18. The new diff is calculated as the sum of same and diff, multiplied by k minus 1, resulting in 48. Same is updated again to the value of prev_diff, which is 18. Finally, the total number of ways to paint the fence is determined by adding same and diff. Adding 18 and 48 gives us 66, meaning there are 66 ways to paint 4 posts with 3 colors while following the constraints. Now let's consider another example, where n equals 5 and k equals 2. With 5 fence posts and 2 colors, we start by checking the base cases. If n is 0, there are no posts to paint, so the result is 0. If n is 1, we can paint the single post in k different ways, which would be 2. Since n is 5, neither of these cases applies. We then move to initialization. Here, same is set to k, or 2, and diff is calculated as k multiplied by k minus 1, which also evaluates to 2. In the iteration step, for I equal to 3, prev_diff is set to the current value of diff, which is 2. The new diff is calculated as the sum of same and diff, multiplied by k minus 1, which evaluates to 4. Same is updated to the value of prev_diff, which is 2. For I equal to 4, prev_diff is updated to the current diff, which is now 4. The new diff is calculated as the sum of same and diff, multiplied by k minus 1, resulting in 6. Same is updated to the value of prev_diff, which is 4. Finally, for I equal to 5, prev_diff is updated again to the current diff, now 6. The new diff is calculated as the sum of same and diff, multiplied by k minus 1, which evaluates to 10. Same is updated to 6. The total number of ways to paint the fence is determined by adding same and diff. Adding 6 and 10 gives us 16, meaning there are 16 ways to paint 5 posts with 2 colors while adhering to the constraints. To analyze the time complexity of this solution, we can break it down into several steps. First, the base cases, such as checking if n is equal to 0 or 1, are simple conditional checks that take constant time, or O1. Next, the initialization of variables like same and diff also involves basic arithmetic operations, which again take constant time, O1. The main computational effort comes from the for loop, which runs from I equals 3 to I equals n. This means the loop executes n 2 iterations. Inside each iteration, we perform a fixed number of simple arithmetic operations to update prev_diff, diff, and same. Since these operations are O1 per iteration, the total time spent in the loop is proportional to the number of iterations, or O(n)(2). Simplifying further, this becomes O(n). Lastly, the return statement involves a single arithmetic operation, which is O1. Adding all these together, the loop dominates the overall time complexity, resulting in O(n). When we combine all the steps, the overall time complexity of the algorithm is determined by the loop, which is O(n). Moving on to the space complexity, the analysis is straightforward. The algorithm uses a constant number of variables, same, diff, and prev_diff. Each of these variables occupies a fixed amount of memory, regardless of the input size, which means the space complexity for these variables is O(1). Additionally, the solution does not rely on any extra data structures, such as arrays or recursion stacks, that would scale with the input size. Since the memory usage remains constant and independent of n, the overall space complexity of the algorithm is O(1). To put this into perspective, let's compare the optimized solution to a naive or brute force approach. A naive approach might involve generating all possible ways to paint the fence and then filtering out the invalid combinations where more than two adjacent posts have the same color. For n posts and k colors, this would result in k(n) combinations to evaluate, leading to an exponential time complexity of O(k) to the power of n. Moreover, storing all these combinations would require O(k) to the power of n space. In contrast, the optimized approach uses a dynamic programming recurrence relation to calculate the result efficiently. Specifically, it tracks same and diff states, where same I represents cases where the last two posts are the same color, and diff I represents cases where they are different. By updating these states iteratively and only keeping the last two values, the optimized solution reduces the space complexity to O(1) and the time complexity to O(n). To solidify this understanding, let's summarize the mathematical proof for the big O analysis. For time complexity, the primary driver is the loop, which runs end 2 times, with each iteration performing O(1) operations. This gives O(n)(2), which simplifies to O(n). All other operations in the algorithm, such as initialization and the final return statement, are O(1) and do not influence the overall complexity. Adding these together, the total time complexity is O(1) plus O(1) plus O(n) plus O(1), which simplifies to O(n). For space complexity, the algorithm uses a fixed number of variables, regardless of n, leading to O(1). Finally, since the algorithm processes the input linearly, there is no variation in performance across best, average, or worst cases. The time complexity remains O(n), and the space complexity remains O(1) in all scenarios. One common mistake when solving the paint fence problem is ignoring the constraint that no more than two adjacent posts can have the same color. If this rule isn't enforced, the solution will fail for cases where this condition is violated. It's crucial to ensure that your recurrence relation or logic explicitly incorporates this constraint. Another frequent issue is misinterpreting the problem for smaller values of n, like n equals 1 or n equals 2. For example, when n equals 1, there are k valid ways to paint the post, but for n equals 2, there are k² combinations since each post can freely choose any color. Overlooking these edge cases often leads to incorrect results. Additionally, errors in defining the recurrence relation are common, particularly when distinguishing between scenarios where the last two posts share the same color versus when they have different colors. You need to clearly define these states to avoid such pitfalls. Lastly, some implementations use brute force to generate all possible combinations, but that approach is computationally expensive, with a time complexity of O(k) to the power of n. For larger inputs, this becomes impractical, so optimizing with dynamic programming is essential. Another challenge involves handling large constraints effectively. For instance, when n and k are as large as 10 to the power of 4, failing to use modulo arithmetic, such as mod 10 to the power of 9 plus 7, can lead to overflow errors. It's important to account for this in your implementation. During interviews, it's helpful to break down the recurrence relation into two cases, one where the last two posts are the same color and another where they are different. This demonstrates your ability to analyze the problem comprehensively. You may also be asked to discuss the time complexity trade-offs between brute force and dynamic programming approaches. Highlighting how dynamic programming reduces the complexity to O(n), and discussing space optimization techniques, like reducing the DP array to just 2 variables, can leave a strong impression. Handling edge cases, such as n equals 1, k equals 1, or scenarios where n is much larger than k, is another area interviewers often probe. Lastly, connecting the problem to practical applications, such as scheduling tasks or graph coloring, can showcase your broader understanding and relevance of the solution. The paint fence problem shares similarities with several other problems, which can help deepen your understanding. For instance, LeetCode 198, the house robber problem, involves using a recurrence relation to solve overlapping subproblems within a linear structure. Similarly, LeetCode 213, house robber 2, adds an additional constraint with circular houses, which is akin to restricting adjacent colors in the paint fence problem. Of course, LeetCode 276 is the direct problem we're addressing here, but variations of the constraints can create new challenges. Another related problem is LeetCode 70, climbing stairs, which serves as a foundational example of solving problems with recurrence relations. This problem, while simpler, is a great starting point for understanding basic dynamic programming concepts and applying them to more complex scenarios like paint fence. There are alternative approaches to solving the paint fence problem, each with its own trade-offs. A bottom-up dynamic programming approach iteratively fills a DP table, achieving a time complexity of O(n). The space complexity can be reduced to O(1) by storing only the last two states instead of maintaining a full DP array, making it both time and memory efficient. However, this approach requires precise definitions of the recurrence relations to ensure correctness. A recursive approach with memoization follows a top-down methodology, caching the results of subproblems to avoid redundant calculations. While it also has a time complexity of O(n), it uses additional memory for the recursion stack, making it less efficient in terms of space. Lastly, mathematical combinatorics can be used for small cases, offering direct formulas to calculate results without iteration. This method is elegant but not scalable or practical for larger inputs, as it becomes difficult to generalize for all edge cases. Choosing the right approach depends on the specific constraints and requirements of the problem. Great job following along. To summarize, we explored how to efficiently solve the paint fence problem using dynamic programming, focusing on optimizing both time and space complexity. Remember, dynamic programming is a vital skill for tackling complex constraints. Keep practicing, and don't forget to like and subscribe for more tutorials. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!